Alright guys, let's review oxidation of unknown alcohol multi outcome experiment. Firstly, oxidation refers to the loss of hydrogen or addition of oxygen, right? You may use this as a criteria to judge whether it's an oxidation reaction or reduction reaction. Secondly, we're going to talk about reaction equation. To balance an equation, you need to have all starting materials on the left of the arrow and all products, including byproducts, on the right of the arrow. At the same time, you will provide the reaction condition as well as catalyst needed on top or at the bottom of the arrow. You also want to make sure that the number of atoms equate on the left and on the right of the arrow, right? Because you're writing an equation, so it has to equate. The reaction follows two steps. The first one will be formation of an oxidizer. So we started with sodium hypochlorite. Sodium hypochlorite to react with acetic acid and form hypochlorous acid, which will be acting as an oxidizer, right? Is this equation balanced? No. If you count, you will realize that there are 3 oxygen atoms on the left, and there's only 1 on the right. So you need to balance the equation. After exchanging of the anion and cation, you will come to the conclusion that sodium acetate will be the byproduct, right? So that's a balanced equation. The second step will be using the oxidizer, hypochlorous acid, to oxidize an unknown alcohol, right? We know the product is going to be either unknown ketone or aldehyde. So what's going to be the byproduct? If you compare these two starting and final product, you'll realize that the difference will be 2 protons. One will come from a proton on the left. What's going to be the byproduct then? So you're going to have water and HCl, right? As we mentioned, hypochlorous acid is the oxidizer. So the chlorine will be reduced from +1 charge to chloride, which is carrying a negative charge. At the same time, the carbon will be oxidized from a sp3 hybridized carbon to sp2 hybridized carbon. And now let's count. Does the equation equate? There are 2 oxygens, two oxygens, and then the protons, 1, 2, 3, those equate, right? All right, so we successfully balanced the equation. Do we need anything else? Yes. The reaction happens in ice water. So you either have 0 degrees Celsius or ice bath or ice water on top of the arrow to indicate the reaction condition, right? A reaction was very exothermic, which is why we use ice bath in the first place, to control the reaction doesn't go too violently. Right, that's going to be our balance equation for oxidation of alcohols. So what's happening? Let's talk about mechanisms then. Mechanism, I'm going to use an unknown alcohol. Well, oxygen being a very good nucleophile, is going to snatch away chlorine from a protonated oxidizer, which is hypochlorous acid. At the same time, water is going to be the molecule being kicked off, at the same time producing the intermediate that's carrying a positive charge. We're going to have a base, let's say acetate, to snatch away the proton. Also an intermediate, right? Well, we know you're going to form a carbon-oxygen double bond, which means that you need to eliminate the proton at the same time kick off the oxide, right? Which falls into the category of elimination reaction that we're very familiarized with. We're going to have either acetate or water to do the elimination. Restore double bond, kick off chloride, and give us chloride and CH3COOH as a byproduct, right? Which formed the product that we desired. And this is going to be the mechanism. The next thing we're going to talk about is something we used this week for testing. We used Ki starch paper twice. And why do we use that in the first place? How does it work? To figure that out, you will need to know what's happening during the Ki starch paper testing process. There is a saccharide called amylose in starch that will change into a dark blue color or purple color when encountered with iodine or triiodide. So basically, we're going to use this characteristic of starch to tell whether the iodide anion will be oxidized into iodine or triiodide or not. So there are 3 species involved for iodine molecule, right? For the element, sorry. First one is iodide, which is an anion that's carrying a positive charge. It's going to be the reducing reagent, right? That's able to be oxidized. The second species is called it's a diatomic molecule. It's called iodine. That's a molecule free of charge. It's a very good oxidizing reagent. When coming to triiodide, so firstly, it's an anion, right? It's carrying a negative charge. Secondly, you can kind of see that as the combination of a molecule and also the anion. At the same time, it's a pretty good oxidizing reagent. All right, so as we said, amylose in starch will turn to a dark blue color with the presence of the oxidizer, with the presence of iodine and triiodide. And what's going to happen is that originally in Ki starch paper, there's only iodide anion, right? The reducing reagent. After it's being oxidized with the presence of oxidizing reagent, it's going to change to either the molecule or triiodide. That is going to make starch change color to a dark blue color. So basically, the presence of starch will only change color if you have an oxidizing reagent in your solution, right? It's an indicator of the presence of oxidizing reagent. What can be counted as oxidizing reagent? Hypochlorous acid is one of them. Sodium hypochlorite is another possibility, right, in our solution mixture. All right, the next thing we're going to talk about is quenching solution, or the quenching process, I would say. We used sodium hypochlorite as a quenching solution. So what are we quenching in the first place? Sodium hypochlorite with sulfur carrying a +4 charge, right? Because oxygen carrying a -2, proton is a +1, sodium is +1, which gives us sodium as +2. We also know that sodium have 16 electrons on the outside shell, which equals to 2 plus 8 plus 6. On the very outside shell of sulfur, there are 6 electrons that can be lost, which will give us plus 6, right? That's a maximized charge for sulfur. It also means that our sodium bisulfite can be oxidized into sodium bisulfate, which is carrying a plus 6 charge. So basically, we use sodium hypochlorite, right? Sodium bisulfite to reduce the presence of oxidizer and lead to the formation of bisulfate, right? If I ask you to write out an equation, it will look like it will look like bisulfite. Let's see what we have. We have sodium hypochlorite 4. What's going to be the byproduct? So you have an addition of oxygen here that's coming from sodium hypochlorite, right? As we mentioned, the loss of oxygen, the addition of oxygen, which will leave you sodium chloride as a byproduct. If you treat hypochlorous acid as a reducing reagent, the product will be the same, and HCl as a byproduct, right? Either way, that's a correct form. That's a correct equation. Well, sulfur being the one oxidized, chlorine will be the one that's being reduced, right? Sulfur got an elevation of 2 charges. At the same time, chlorine were down 2 charges, which also equal to each other, right? That's also another way which can help you to confirm whether you balance the equation or not. And now comes the question, what kind of the solution can be used as quenching solution and what cannot? Well, you want to quench to reduce, right? So it has to have some kind of reducing functions. How about sodium nitrate? Nitrate, sorry. It's carrying a plus 5 charge, so it's at its maximized charge, right? Nope, it can't, because it's not a reducing reagent. How about sodium chloride? Can it be reduced? Nope. How about sodium bisulfate? That's a product, right? Of course, it cannot be further oxidized. How about sodium sulfate? It contains a charge of, that's a -2 plus 1, a plus 6. So sulfur is again at its maximized charge and cannot be fully oxidized, further oxidized. How about sulfite? Plus 4 seem to be okay, right? You can treat that the same as sodium bisulfite. How about chlorine? Nope, chlorine cannot. It's a pretty good oxidizer, as a matter of fact. How about sodium sulfide? Sulfur is at -2. Yes, it can be oxidized again, which make it a suitable reagent acting as quenching reagent. Okay, it's going to be oxide to sulfur. Right. I also see some in the post-lab questions where when students are writing equation, they wrote +2 sodium bisulfite, which give us chlorine. Firstly, chlorine molecule will react with water pretty readily to give you HCl, hypochlorous acid. Am I balancing it? Yes, that's a balanced equation, which means that it's going to be, again, give you hypochlorous acid, which can be reduced again, right? So if you write chlorine as a product, then you have an incomplete reaction, which is why I took points off. Right, the chlorine will be directly directly reduced into the chloride. Yeah. All right, last but not the least, we'll walk through what's happening in the reaction progress so that you can refresh your memory, okay? That's gonna be a 6. If I ask you to design the reaction process, you will need to have a general idea of what's happening and why we're using this reagent. And also, you may want to know how to use FTIR and proton MR to analyze or to identify the unknown you used. All right, so we add bleach, acetic acid, and unknown alcohol together, right? The first thing that's going to happen is going to be these two forming the oxidizing reagent, HClO, R, and R alcohol. If I ask you to design the experiment, the first thing you want to make sure is to have one of the products to be in excess to make sure the other one goes to completion, right? To go through exhaustion. In this reaction, you would want your alcohol to be fully oxidized. So you will make the acid and sodium and the bleach to be in excess, which gives you excessive amount of hypochlorous acid, and there might be some of those left, right? Since you have, a lot of those. That's our second step, mixture. Oxidizer reducing reagent. The redox reaction going to happen, right? At the same time, carrying was being in excess that didn't react. So it's going to form the byproduct, water, and desired product, which is the aldehyde or ketone redox reaction. What's going to happen next? Or what did we do next? We are testing using Ki starch paper. As we know, the presence of oxidizing reagent, and some unreacted hypochlorous acid will change the starch to a dark blue color, right? And the next step will be adding sodium bisulfite to react with the excessive amount of sodium hypochlorite and hypochlorous acid, which will give us sodium chloride, sodium bisulfate, water, and again our product, which will remain in the solution. We add a little bit of sodium hydroxide to neutralize our acid again, right? I'm gonna carry all those down. H2O, sodium bisulfate, sodium acetate, and desired product. We also tested again after the sodium bisulfite step using Ki starch paper. And this time, the solution will remain colorless or unchanged because there shouldn't be any oxidizing reagent left, right? And last but not the least, we use DCM or dichloromethane. They're the same thing. It's an organic solvent to extract the desired product into organic layer. All the ones I circled out are very good ionic compound that will dissolve in water. rather than going into organic layer, right? So in that case, we get rid of all of those. And we use sodium sulfate to dry the solution and evaporate off DCM as a extraction solvent, which will give us the pure product. And then you will go through IR and proton NMR analysis. If I provide you with an IR and proton NMR of the analysis of the final product, you will need to be able to identify what it is based on all the information you will get. So I would definitely go review these two methods as well.